Welcome to this little experiment I've got for you on intermolecular, or what some people call interparticle forces. This was developed by Dr. Tom Kunzelman up in Michigan. Great guy and a great teacher. Here's the straw. Put it in the liquid. Pull it up. Nothing, not much happens. Put it in here. Starts to change colors. Okay, changing color. Gone. Okay, so I know you can see it there, but definitely changing color. Okay, so what's going on? Let's take a closer look. Okay, so to explain how this works, I'm going to give you a little bit of a clue. First of all, I had let me get my studio here fixed. I had two different chemicals. In one of them, there was water, which we actually have modeled over here. Okay, so here's a model of water as a gas. Okay, and what we'd like to look at are all of the intermolecular forces. Of course, water is going to have a lot of hydrogen bonds. It's a very polar molecule, so that's like dipole dipole. And also because it has a mass to it, there's also a little bit of dispersion forces. Now, what this can do is this will maximize what happens. So I'm going to click over here and say optimize model. Now watch what happens. We're going to let that go. And one of the things that it shows here, it shows the total potential energy that would have to be overcome to spread all of these things apart over here. Okay, so every one of those lines, when you see the green line, that's hydrogen bonding. When you see the blue line, it's the dispersion forces. And then when you see the purple line, it's the dipole-dipole between those four molecules. And they all combine. And what that says is that if I want to pull those apart, I need to overcome this much energy. So now what we're going to do is we would like to, and you can see here, this is the big hump that we need to overcome. So now I'm going to tell you what was in the other test tube. In the other test tube, there was a molecule that looked like water, but it wasn't. And let me show you what it is. So we're going to reset all this, get this out of here. Let's clear the model. And again, you can do this on Adam Smith. This is a really powerful tool. Of course, now it's starting to lock up. So let's see, let's go over here. And I'm going to have to hit pause and I'll get back to you. Okay, so now we've got what was in the other little test tube I had, and that was methanol. And methanol is similar to water. If you look here, it's got an OH, so we would predict that it has hydrogen bonding. But because it only has one OH, and it's not H2O, it probably doesn't have as much hydrogen bonding. And because it has carbon and CH3, that makes it a little more nonpolar. You might predict maybe a little more dispersion force, not quite as polar, maybe not less dipole-dipole because the electronegativity isn't as big and changes, and probably not as many hydrogen bonds. Let's optimize the molecule and see what happens. So of course this goes together, and when we go in, you can see here that how these are all of those interparticle and intermolecular forces. A lot more dispersion forces. There's a lot more blue, not as much purple, and not as much green. But when we look, though, look at the difference right here. Okay, the amount of this we'd have to pull apart, that energy we would have to put into it, it's not quite as high as the stuff with water. Now, with that in mind, let's see if we could revisit our experiment and figure out what's going on in there. We're back. Now, here's the secret to how this little trick worked. This straw that I have here, it actually, you can get these at, different stores. It changes color based on temperature. So for instance, glass of ice water, room temperature straw, stir it up a little bit, presto, changes colors. Now, with that being the case, why did it change colors with our two liquids? Okay, so first of all, here's water. The model shows there's a lot of intermolecular forces for a small molecule. Fair number of dispersion forces. It's very polar, dipole, dipole, lots of hydrogen bonding. I put it in here, I take it out, and it's hard. It takes a lot of energy to make the water evaporate. Okay. Evaporation goes from a liquid to a gas. You have to overcome all those little lines of force. It steals the energy from the straw if it can, and that's why it gets colder. That's why evaporation is a cooling process. Doesn't evaporate, it's still wet. Okay. On the other hand, let's take our methanol, stick it in, stir it up a bit. All I have to do, you can see it changing color right. And again, there it goes, it changed colors. Why? Well, the methanol, it evaporates faster, less hydrogen bonding, maybe less dipole, and it steals the heat, which means it steals the heat from the straw, overcomes those few forces. It takes off as a gas, changes the potential energy, climbs out of the well, and because it stole the heat from the straw gets colder. It loses heat. That means colder. It means it lost energy. That's the key. So in the lab that we're going to do now, you want to do what we just did. Look at the molecules. Is there a lot of dispersion, a lot of dipole, a lot of hydrogen bonding? Tough to evaporate. Low change in temperature. It'll stay like this side. Less forces, big change in temperature. It evaporates. And I don't know if it's hard to see that, but there's a contrast there. I'll do it again. Okay, see, take it. So fewer forces, change in temperature, gets cold quickly. Like when you go to the doctor's office, get a shot, put some alcohol on your skin, it feels cold. That's why. And that's the key to being able to figure out this lab.